This is a walkthrough of the experiment that studies the effect of altitude on weight and mass. This video demonstration is concerned with the following learning objectives: the relationship between weight and mass, the effect of gravity on weight, the effect of altitude on gravity, the effect of altitude on weight, the relationship between gravity and free fall, and finally, a comparison between a weighing scale and a pan balance. The interface of this experiment features an altitude control panel on the left, which allows you to move a satellite to any altitude of your choice. The satellite can be moved by clicking and dragging it. For now, let us return it to the surface of the Earth. To the right of the altitude control panel is a planet selector. This is a very powerful feature that allows you to put the satellite on a planet of your choice. If you select Mars, you are putting the satellite in the gravitational pull of the planet Mars. By choosing Jupiter, you are exposing the satellite to the gravitational pull of Jupiter. To the right of the altitude control panel can be found several pieces of equipment: a 100 kilogram mass, a weighing scale, a pan balance, and several discrete masses. It is important to note that this equipment is in reality located inside the satellite. The experiment gives you the ability to place the satellite at an altitude of your choice on a planet of your choice to study the effect of the acceleration of gravity on these masses. In the center is a graph which plots the weight of the 100 kilogram mass against the altitude at which the measurement was taken. This graph is automatically generated for every altitude at which the 100 kilogram mass is measured. To the right is the instruction panel. To open the instruction panel, click on the downward pointing arrow, then use the left and the right keys to read the instructions for using this program. To close the instruction panel, click on the upward pointing arrow. Let us now review the interactions that will help us achieve our learning objectives. The masses can be picked up and dropped in order to study their free fall behaviors. Observe the free fall of the 100 kilogram mass and compare that with the free fall of the 50 kilogram, the 20 and the 10 kilogram masses. It is pretty clear that they all fall at the same rate. If we repeat this experiment at a greater altitude, it becomes pretty clear that the free fall happens at a lower rate. At higher altitudes, the rate of free fall is also lower. Further, it can be seen that the rate at which all the objects fall is the same. The rate of descent of the objects depends on the acceleration due to gravity and not on their masses. Weighing the 100 kilogram mass at an altitude of 11,800 kilometers shows that its weight is 121 newtons. This red dot that appeared automatically on the graph is a representation of this reading. Let us now take a few more readings of the weight of the 100 kilogram mass taken at different altitudes. Observe the red curve that is being formed as a result of these readings. The curve is not a straight line. This curve is characteristic of an inverse square relationship. This means that the weight is inversely proportional to the square of the altitude. Let us check if the behavior of the pan balance is any different from the behavior of the weighing scale. At 20,900 kilometers, a reading taken on the pan balance gives us this blue dot. This dot represents the mass of the 100 kilogram body. Let us proceed to repeat these observations at different altitudes. Observe the blue line that is forming automatically on the graph. In correspondence to these readings. In conclusion, at different altitudes, the mass has different weights owing to the different rates of acceleration due to gravity. However, at different altitudes, it always has the same mass. The body does not change its mass, but it changes its weight depending on the altitude. Let us take a couple of measurements to make the relationship between mass and weight more clear. Let us return the satellite to the surface of the Earth and weigh the 100 kilogram mass. 100 kilogram mass has a weight of 980 newtons. A 10 kilogram mass has a weight of 98 newtons. Notice that when the mass is a tenth, the weight is also a tenth. Further, the weight is 9.8 times the mass. This can be verified with the 50 kilogram mass. 50 kilogram weighs 490 newtons, which is 1/2 of 980 newtons. To further verify this fact, making the mass 100 kilograms reinstates the weight at 980 newtons. From this we can conclude that the mass times 9.8 translates to the weight of a body on Earth. Further, 9.8 represents the acceleration due to gravity on Earth. Trying this observation on Jupiter will lead us to find the acceleration due to gravity on Jupiter. 100 kilograms weighs 2,312 newtons, whereas 10 kilograms on Jupiter has a weight of 231 newtons. The acceleration due to gravity on Jupiter is therefore 231 divided by 10, 23.1 meters per second squared. The same measurements can be taken on any of the other available planets, on Neptune, on the Sun, or on Venus, in order to show us the relationship between mass and weight, between weight and acceleration due to gravity, and between altitude and acceleration due to gravity. These interactions help us achieve the learning objectives that were set out at the beginning of this experiment. Thank you.